All right, what is up, everyone? Welcome to week 110 of building my own operating system. Thanks a lot for tuning in. Let me start. Today we are continuing to work on scheduling, which has been a very exciting topic so far. So last week we made some more progress and were able, for the very first time, to get multiple kernel threads to execute, switching back and forth and saving and restoring their state. So that was a pretty good piece of progress, and we're just going to keep it moving with that today. So as usual, test 0 in the chat. Chat widget is working today. It's a good sign. And let's just see. I think we're almost pretty much set up to get the stream started. Word. All right. What's up, Nightwalker? Thanks for joining. Nice to see you. Okay. Nightwalker is here. Awesome. Very cool. Very cool. So let's just sort of ease into this. Here is what the kernel looks like. Got our kernel running. Hello from task 1 and 2. It switches back and forth, and it's just printing out some numbers. And this is looking okay, but the problem is that after a while it starts to get very slow. I think it takes around 600 by the time it gets to the number 600 or something like that, each iteration starts to get really slow. It's dramatic. It's very dramatic. Look at how slow that is. And I wonder if stop. I wonder, yeah, we're using 2% of the CPU, which is really not that much. So that's just interesting, just in case. Yeah, I'm not quite sure what I was looking, but just to observe the external behavior of Kimu in this situation. We're not using a lot of CPU, so that suggests there's a problem within the kernel somehow with the context switch or something like this. So to me, that's the primary topic. That's the primary interesting thing to look into today. What could possibly be causing the slowness? So we're just gonna update this little roadmap. So we got the basic context switching working, and so now here were just some ideas, but pretty much the most important one right now is this weird bug. Stuff like that. So let's look into that today. What is up to the 11 people in the chat right now? Thanks for joining, everyone. So I'm just going to need to think about how. So obviously we can read the code and try to find the bug. Using debug prints, maybe also timers, timing. The thing, we don't really have any timing in the OS right now, and so instruction. So I think all we would be able to do is use maybe something like the read TSC instruction or something like that to maybe get some timing information. Not sure how accurately Kimu does that, but let's just kind of get that reproducing one more time. And actually what I'll do, I'll get it, let's just run it under the debugger. What's up, Alonis BRB? Bro, can you share the GitHub link? There is currently no GitHub link. I haven't published any of this yet. I have some plans to, and so I would just ask if you're interested in hearing more about the GitHub release. Sign up for my newsletter, and I'll be sharing some updates there about that. It also helps me just know like how much interest is there in that really. So task 1 and 2 are running. Oops. So what's my change here? I have this comment and another comment. Okay, while it's going, I'll just quickly fix that up. Okay. So now we've reached the point where things are getting very slow. And it's probably something pretty simple. I'm just going to randomly interrupt. So it's in this sleep, which probably makes sense. So I'm just trying to understand. No, we went kernel HPP. I'm just trying to, I don't know what the problem is, but these kind of stupid loops are there just as a really simple way to sort of like slow things down. I wonder if somehow that's causing a problem though, these like stupid iteration loops. Let me, so if I just run things like this, it's going to run much faster. Oh, why did I quit? That was, okay. Continue. So let me also kind of characterize the situation we're seeing. So we were problem in debug mode with the stupid for loop sleep strategy. We were seeing it get very slow after reaching number 500 or so. Approximately, I don't know, 45 seconds of running. debugger break. Randomly, we broke inside the for loop. All right, so this is still going. It's going pretty fast. I think we're not really seeing that issue from before. Although maybe it's a little bit hard to tell. Yeah. What's up, digitalized? My guess is race condition that triggers under the perfect condition. Yeah, that's an interesting idea. I think race condition. The thing is, this issue is deterministic. I'm just gonna take a quiz. So this is when I remove that stupid for loop thing. So, yeah. What's up? What's up? Windows 1.0. What's up? Cat Flare in the house. Remove the stupid for loop. The problem seems to disappear. And I guess what would we really expect to be seeing? I guess if the problem were still happening, I guess this would just get really slow. And this has been running for quite some time now, and I'm not really seeing a slowdown. So I'm also curious what the... Okay, I'm gonna not enter my password on stream. Okay. What is... Just out of curiosity, it's interesting that Kimu is still... Is this even accurate? Kimu is only taking 2% of the CPU. My terminal is taking more CPU than Kimu. Something about that does not really make sense to me. I load up the activity monitor. Okay, hopefully I don't dox myself by showing my process list, but this is much closer to what I would expect to see. Sorry, what just happened? Okay. 100% CPU on the Kimu process. I feel like HTOP is buggy or something like that, so I'm gonna not trust that maybe. So this is a bit more expected. It's interesting that my terminal is taking up so much CPU time. You can see the cursor like wiggling back and forth. I guess it's just there's just so much output coming from this process that it's constantly re-rendering this frame. Maybe that's the reason. Maybe it's actually a tmux thing. Hard to tell. But I think we can safely say that taking away that stupid for loop made the problem disappear. And so something something with, obviously with that for loop. So up top, Sigma, which MacBook are you using? 14 or 16 inch? Mine is 16 inches. Digitalize, maybe the sleep is blocking too long. Maybe. Sleep is blocking too long. Okay, I think I feel... I don't know, I think it's maybe hard to tell if it's like really... I mean, it seems to be working well. You can't really see the numbers incrementing, but if I just kill things, these numbers look exactly like they should be. They are constantly matching. 21, 20, 19, they're in these pairs, and so that's looking good. So I think the whole point of this investigation is it's possible that this is some kind of red herring. It's possible that this stupid way of sleeping, like what would the problem be? My theory is that there's some problem with this, with this style of sleeping that is causing, maybe it's causing Kimu to specifically react in a strange way and slow things down. It's pretty mysterious. But I think the takeaway is to not really get too hung up on it. I'm just going to go ahead and run this one more time. We can also try, we can also try a slower sleep. So that's going. We'll let that cook for, actually, let's take a look at the activity monitor while that's running. So Kimu is taking 100% CPU, which is totally expected. And I am curious, I'll answer the question in just 1 second, digitalized. There's some specific drop-off point. It was like 690. And the Kimu CPU percentage goes much slower. So my theory is that I don't know if there's some kind of CPU throttling logic or something like this in Kimu, but yeah. Oh, what's up, useless? Let's just ask the AI. When I run the kernel in Kimu, strangely, when the threads reach around 690 iterations in the print, the performance, I don't know how do we say this, the performance speed radically changes and the kernel seems to run significantly slower. If I remove the for loop entirely, this does not happen. Is it possible that these long for loops are triggering some kind of throttling either at the Kimu level or possibly even the CPU running on ARM? I don't even know, like ARM M2 MacBook Pro. Let's just ask the AI this question. We got a stacked chat today. What's up, Checkwab? Have you checked the something of those delays? No, I have not done that yet, because I'm not really sure what I would expect to see there exactly. Visualize my current goal with the scheduler, and so I'm working towards cooperative scheduling right now, where we can have kernel threads. Weird. Okay, I've suggested some halts. Yeah, basically, I'm trying to get to the point where we have, cooperatively scheduled kernel threads, and then probably after that, probably getting to preemptive scheduling, and so it's just sort of a, checkpoint by checkpoint. For me, cooperative kernel threads was the first step, and then probably once that's going, we can start doing preemptive scheduling. We can get the timer interrupt going. Yeah, stuff like that. I also want to be designing ahead of time to support multi-core and make it like interrupt safe and stuff like this. And so that's the goal. I think we have some problems in the implementation currently with the way the context switch works in terms of how we're stashing like the register state in this like weird global buffer. That's what we kind of did last time to get it working, but I was talking to the AI and it was like, okay, there's some problems with that approach. So there's some other concerns we'll have to deal with. What ideal scheduling algorithm are you thinking of? I think so. I'm not really that concerned with scheduling algorithms right now. That's one of the less important things to me. I'm happy to do a round robin scheduler for now. We could think about doing some kind of priority based scheduling. I mean, I don't actually even know the scheduling algorithms like that well, so I don't even know. So for me, I'm happy to stick with round robin for now, and work on the other parts of the kernel. So let's see what the AI said. Host thermal throttling. The bare for loop is doing nothing but burn CPU cycles. Kimu sees a guess tightly. The host CPU pegs at 100%, and after sustained load, macOS's thermal governor throttles. Why halt fixes it? When the guest executes halt, Kimu suspends. So it's okay. So I think basically the confirmation is that by sleeping in this way, we trigger the throttling on my laptop. Yeah, and so that is interesting to learn about. And it just means that I don't think that slowness was because of a bug in the kernel implementation. That's really the main point. The main point here. Let's just take, so it's like but it's suggesting to do a halt. I don't think that's what we want. So because the halt instruction, if I understand it, it suspends the CPU until an interrupt arrives. The problem is we don't really have interrupts. Like interrupts are not really firing on the OS right now. We do not have a timer interrupt. Period. So just out of curiosity, I think this AI produced a wrong solution, and so after 20 seconds we'll just check it out. Give me 1 sec. Okay, so let's say you're at your kernel development job. The AI just recommended that you put some halt instructions into your code. We think it's wrong, right? We think that this is actually a bad suggestion because there's no interrupts in our kernel. And so what's going to happen is that we're going to hit the halt and the kernel is going to fall asleep forever. That's my theory. And I'm curious if that is a correct understanding. I think another giveaway that it's not a problem with the kernel is because it's such a step change difference in performance. Like, it's not like it gets slower the more numbers there are, I think. Although it's hard to tell. It like went from just like one speed to like a lot slower, but both were sort of semi-consistent, I want to say. So let's kill this. And so here's my theory. The kernel is just going to hang forever. Let's just see if I'm right. Yep. I think that's what's going on. So don't trust I mean, it sort of slightly gave a caveat about its solution, but ultimately it was incorrect. And so I'm going to undo all these changes. Could do like a wall time test with a basic bash script. Also, sounds cool. Hopefully I get my RTOS here soon in a few weeks and we can learn something from the stream. Well, we can do an exchange. I'm sure I could learn something from you too. Yeah, I think I sort of have it in mind to do something a little bit more RTOS style with my OS. I'm interested in making it very preemptible, like making sure the kernel execution is preemptible. I'm also interested in doing things more like how preempt RT in Linux does it, where interrupts can get deferred into kernel threads, and spin locks are replaced with mutexes, stuff like this. All of that stuff relies on a very solid core of making sure your kernel threads are preemptible, and that's exactly what I'm trying to work on right now. And a big part of that is making sure that kernel execution can yield and save its state. And so that's a key part. I think I didn't understand your suggestion. You could do a wall time test with a bash script. Do you mean something like just like timing how long it takes things to run? Yeah, just thinking about that. Okay, but I think we solved the first mystery. I think if we can trust the AI, it is explaining. Okay. So with that said, let's see how we want to move on here. Moving on. And so there's a couple so currently we only have 2 kernel tasks. Moving on, we can try having much more than 2 kernel tasks. For example, we can also kind of keep fleshing out the scheduler interface. And so currently, tasks cannot do very much, if anything at all. They can log things, and they technically have full access to the kernel. In particular, their options are kind of limited. They can yield to the scheduler. Yeah, what's up, Shadamanan in the Twitch chat? What's up? They can yield to the scheduler. But notably, there's no way for a kernel task to finish or like exit itself. It just simply does not have that capability. And so that would be interesting, adding kernel thread exit. Another way to state it is that a way to move forward is just to flesh out the set of, it's not quite system calls because everything's in the kernel, but like APIs that kernel tasks have for manipulating just their own lifetimes. Like you can yield and you can exit. Probably those are some of the most basic primitive operations. And so yield, like adding an exit, probably is an important thing to figure out. We currently do have we have a couple APIs. I think I've actually did sort of sketch it out. Exit, current, task, and yield. I think I slightly sketched it out. And we'll need to see. I think I never actually tested that. There's the create task API, which you can use for creating some kernel threads. I don't know what my terminology is going to be yet. Tasks or threads. Task is sort of like the classic terminology, like Linux uses this, which I think it comes from the x86 documentation, which like talks about tasks, but threads might be a little bit more just direct, because that's really what we're doing, like implementing threads. So but there's other things to do, and so let's just document this. This was likely CPU throttling. Okay. The idle thread. So that's also an interesting topic. The idle thread. Making sure that there's always at least one thread that can run on the system. And I guess the vision that we're kind of working towards here is the vision for our basic kind of MVP of cooperative. Written for MVP of cooperative scheduling. Tasks can be dynamically created. They can yield. They can exit. Stuff like this. And then from there, it'd be kind of cool. We can build things like a mutex. Building off of these scheduler primitives, we can build our first mutex. Build our first mutex using these primitives. That would be kind of a cool thing to play with. What are the other problems? So in general, the context switch is still kind of questionable. Let's check out the context switch. Scheduler.s. Okay. Our approach is questionable. It nominally is working right now, where when a kernel thread wants to yield, it calls the yield function or method on the scheduler, which is kind of weird. It really is this like naked function that jumps directly into this assembly stub, because it's very important that we do not execute any code that can overwrite a register, because it's important we want to kind of freeze and preserve the running execution state. And so we cannot even execute, we want to be very, very careful to not execute any instructions that can write to any register. And so that's I've done this like naked function yield thing, jump thing, but it ends up here. And then what we do is we save all the registers into this global scratch area, which I have defined somewhere. Here, it's in this. There is a global object that contains storage for all the registers. And so the first thing we do is just immediately just save like basically everything, just to make sure we don't accidentally lose a register. Then a couple of things are a little bit more tricky to save, like the RIP and the RSP. We do that. But there are problems with this. I was asking the AI about this. But the particular solution of global scratch space is usually a trap in a preemptible SMP kernel. The canonical pattern is closer to what a hardware interrupt does, saved to a per task or per CPU context structure using a stack you control. Okay. There's a bunch of info here. And we could read it. It's a little bit detailed. The point is this design of the global scratch area has some specific problems. It's not re-entrant, I think. Yeah, it's not re-entrant. If you take an interrupt while in the yield stub, you can overwrite the scratch area. This problem is not quite as relevant because it'll be per CPU. And then, yeah, I don't know. It's like global state. And so apparently there are solutions. There's better ways to do this. Right. And so there's some mitigations for some of these problems. Like, okay, it's not SMP safe. And so, yeah, let's make it per CPU. And okay, it's kind of not interrupt safe, but you can just disable interrupts. But like disabling interrupts is not really an ideal solution. At least it's nice to think about other ways that would allow us to not disable interrupts. And saying the global scratch can be okay if it's not end state. Canonical shape safe. And so before we read into that, basically I'll just take a note. What something we could do is I'll just call it actually make the context switch safe. Currently our global scratch area solution is broken and flawed because I didn't think about interrupts. Implement the AI solution for improving this. So yeah. So these would be the main options for what we could do. And really, I mean, this is really just the most important. These are all somewhat surface area things that this is just like the kernel is like just broken right now. And so I think it's worth diving a little bit deeper into actually trying to fix this. And so probably I think that's what we'll do. So I'm just going to take a sip of water. Then we'll get into this and understanding. We're going to read through this. We're going to understand why my current solution is broken, and then we'll also understand what kind of solutions we could imagine that solve the problems. Give me 1 second. Okay. I got the standing desk today, which feels kind of cool. Usually I'm sitting, but it feels kind of nice to be a little bit more mobile. Okay. So let's read through this a little bit. This is from an AI question I asked. And as a bit of a context, I was asking the AI about, like, one of the things we were talking about last stream is like how safe it is to use the stack. I think NSG was proposing that instead of moving things into a global scratch area, we just push things onto the stack. And I was worried about accidentally overflowing the stack. But it sort of seems like trying to avoid overflowing the stack in this particular situation means that the kernel is already in a very bad state where there's extremely little stack left. And so that's already basically a buggy state. That's what I got from the AI. Okay, let's read this. And so global scratch area is okay as a bootstrap hack, but it's not the end state. The canonical shape save into a task context struct, not onto the stack. Right, so basically what's going on right now, maybe I'll try to illustrate it a little bit, is, how can I illustrate this? We have, do I have any other diagrams? Okay, so we have this buffer of tasks. You know, I'll use the sticky instead. We have our container of tasks. Okay. And within the task, there is this, within the task struct, there is this area for the registers. And that's where we can store the register state and also restore it from on context switch. And so, and then maybe also to illustrate. And so we also just straight up have the CPU. Straight up, we just have the CPU, and it also has copies of the registers. And this is what's actually executing, right? And so the CPU is running. We hit the yield. And the current solution is, I'll say this. Then we have the global scratch area. Can I send it back? And so what? So the global scratch area, and then the question is, why do I have the global scratch area? I have the global scratch area because it's really easy to find it. It's like, yeah, it's just when I'm writing this stub, it's very, like, the first instructions are very constrained. I can't use any registers. I need to be very careful to not write to any registers. And so the reason it seemed like the global scratch area could be a good solution is because I could have, like, basically effectively a global pointer, and then it's just trivially easy just to find this thing and then start saving things in there. And so the flow is like, okay, the registers are copied into here. And then we go into this thing called the scheduler return back to C++ entry point, which is right here. And now that we're back in C++, we can more comfortably, we can locate the current task, which is this thing. All right, 20-second break, be right back. Yeah, we can locate the actual task thing, which is what we do with this current task function. And we can copy in the scratch state into the register state. So this is the general flow, because ultimately we need to get the stuff in here into here safely. And by introducing the global scratch area, that is just a very convenient way to just easily copy stuff in. And the quote unquote advantage, maybe it's not a real advantage, is that advantage, no stack is used in this technique. Don't need to worry about overflowing the stack, going beyond the bottom of the stack. But the reason advantage is in quotes is because the AI is saying this is not really actually an advantage. I think, without going into those details, but this isn't really an advantage, because the kernel should simply not be that close to the end of the stack anyway. That is already basically a buggy and very dangerous condition to be in. Because, okay, even if we save a bit of stack space by not pushing all these things, we're still within hundreds of bytes of the end of the stack, which is a pretty dangerous situation to be in. So that would be an alternative. So instead of the global scratch area, alt push things on the stack. And you're using stack space by calling into C++. Yeah, and in fact, that's an excellent point. We are absolutely consuming a bunch of this, consuming arbitrary stack by calling into C++ and calling functions. And so that, you're absolutely right. And so basically that's all reasons why it doesn't necessarily make sense to try to like optimize stack usage this way. So another possible alternative would simply be to push things on the stack. And then pass a pointer to this stack space into the C++ function. So that would basically just be a slight alternative option on the stack. Push things on the stack. Instead, pass a pointer to this. Conceptually the same, still doing 2 copies of the register state, which is not good. Alt idea push things, pass a pointer to this into the CPP. Check wob pointed out that calling into C++ consumes arbitrary stack space anyway. So this optimization to not consume stack space is not well founded. Does your kernel expect a stack red zone? No, I have disabled the red zone in my compiler flags because I understand that in general, the kernel code needs to not use the red zone because interrupts can, when the CPU pushes data after RSP, like that could clobber the red zones. It's important that the kernel always updates RSP as far as I understand. So here's like here would be the slightly alternate idea, but it's conceptually the same, which leads us to basically the other option. I think is what the AI is suggesting. What most kernels do is have a struct context in task-owned memory inside the task control log. Save registers directly into that struct. Switch stacks by resetting RSP to the next task's save stack pointer. Okay, that part I don't quite understand. But let's see. But basically, my understanding is the arrow looks like this. Change the color. This is the other way of doing it. We don't do this copy into some random area, then copy again into the task. We somehow copied, we save the state directly into the task. The problem is how to find the task. So solution 2, save registers directly into the task struct as opposed to separately copying. And maybe it was at a reason. So the rationale here, it's really easy to find the global pointer from the yield SM stub. Basically, it's just a global symbol. So we could save the registers directly as opposed to separate copying. The con, harder to find the task structs. It's a solvable problem, but that's something we'll need to think about. How to find it. Maintain some per CPU global pointer to it at all times, question mark. I don't really know the answer to that. But I also understand that this is a somewhat common strategy, I think. I think Linux calls it there's this global variable called current, which I believe is a pointer to the current task struct or something like that. Yeah. Save registers, switch tasks by setting RSP to the next. So that's, I don't really understand that, to be honest, at all. Switch stacks. Where does that context live? Okay, the context lives in the task struct, always mapped, fixed address, easy. At the top of the kernel stack contains one separate context page per task. Even if you never use pushes to store state, you need a valid stack for code that executes the switch yield path. So this is exactly what checkwap was saying. The extra safety isn't real safety. Yeah. And this is what I just talked about. So per task context struct, we have that, and the per CPU current task pointer. But then the question is, how do we find that current task pointer though? Let's say we're in this assembly. What do we write here? How do we need to find the current task pointer? Without using registers, or we could, or basically the takeaway, we can spill a couple registers onto the stack if it helps us do some computation, I guess, is the point there. But we still need to find this global scratch area. No, sorry, we need to find this global, the context struct. Yeah. The per CPU current task pointer. We need to locate, once we find that, we can start unloading the state directly into that. Yeah. So what? I'm getting a little bit overwhelmed here. This is sort of a lot of stuff to talk about. And I'm trying to think about what a good baby step would be. I mean, so we could try to implement this solution. We could try to have some kind of per CPU current task pointer. And I think I'm still not understanding a couple of things though. And so there's a couple aspects to this problem. So there's a few dimensions here. So it's copies of the registers, and so that's one aspect. And with the global scratch area, we have these like 2 copies, but that's not really the biggest problem. There's also this switch stacks. That's also sort of something to think about. So checkwap FS base or GS base is common. I think, yeah, and that's sort of what we're getting at here. I think it's sort of ultimately a lot of kernels end up converging on storing a pointer in GS base or FS base. Oh yeah, I see. I think that's what, yeah. And so, right, so my question was, how do we find, right, if the question is, how do we locate the per CPU data block containing the pointer to the current task, and check wob use fs.gs base for this. And I think that's actually true. So I think the idea is that the kernel sets up that pointer fairly early on in boot to point to this structure, and then in this code we can already assume that we have this stable register that just always points to this area. That's a good idea, and then maybe we could try to prototype that. Yeah. Just for completeness, what I was envisioning a more convoluted way where somehow spill some registers onto the stack, then use the global kernel pointer to locate the per CPU data block. So it basically just requires a bunch of computation to happen in the stub, which we are really trying to avoid doing. And so that motivates this solution. And for anyone that's like not so deep into like x86 and like FSGS, from my understanding, like at a conceptual level, the idea is that these are just these registers, like FS and GS base are just basically register locations that are available, and they sort of have longer lifetimes than the normal registers. So the general purpose registers are actively used in code gen and are mutated and are semi-volatile, but FS and GS base are architectural registers that don't really participate in the normal volatility of the normal registers, and it's safe to sort of set them and then sort of leave them for long periods of time pointing at, and they're often used to point at these sort of like per CPU or per thread data blocks. So for example, with thread local storage in Linux user space, I'm pretty sure on x86 FS is used to point to each thread's per thread TLS storage area, and I think with the kernel it's a very similar concept where FS and GS. So that's a lot of talking. I think that's the interesting idea. We can even try to prototype that. And so I think I'm still missing some information though, and so I just want to make sure I fully understand the problems. And so switching styles, interrupt safety. Interrupt safety, that was another concern. And so, it's a little bit weird to be referencing this copy and paste. Maybe it's time to go into have the AI actually here help us out. So I'm just going to have it do a bit of a recommendation here. Actually, I'm going to maybe try to dictate this with the AI or something. Can you please help evaluate this design of using the global register scratch area for yielding and context switching? I'm aware that this is actually not really a sound design. It's a bit of a hack to get things working, but I understand that production kernels don't use this type of per CPU scratch state for yielding and rather prefer other mechanisms such as directly saving into the task struct for the thread, and there's some mechanism to actually locate that task struct, for example, using FS or GS, because that was one of the motivations for the global task struct, is that it's easy to find, but maybe there's other designs. And if you could please give in ways that this is unsafe, as far as interrupts or maybe even stack switching. Okay. So I'm just gonna ask the just for overview. But basically, yeah. We can try to prototype the FS thing. What it would look like, we would need to allocate some per CPU storage areas somewhere, and then set up FS or GS space to point there. So let's read about this. And so it's saying, so the problem with this thing, and apparently there's already a comment. Apparently it's a bad idea and broken in the case an interrupt happens and a yield happens during the interrupt. And so what's the problem? So task A is calling yield. We start writing some registers into the context. And then what happens if an interrupt fires during this critical period? Or what happens if the interrupt handler also triggers a yield? It's going to re-enter this code and clobber the in progress yield that was happening. So then the stub resumes and writes the remaining registers, which sort of means it sort of then clobbers that area again. And then now this thing returns and copies corrupt state into task A's. So task A was trying to save its state. And the consequence is that it thinks it did it correctly, but it actually is saving corrupt state. The window is wide. It spans every store from the first move to the call. So this is the window for the interrupt to happen. You need to disable interrupts and re-enable them after the state. Even if this yield, any interrupt handler that calls yield will silently stop the in-flight save. And so, okay, so that's, just so I understand that, I'm just going to move this down. And so, just going to reorganize the notes a little bit. So we're talking about this critical issue. Register save is broken. Yeah. Yeah, shout out to everyone still in the chat right now. I realize this is a lot of talking and not a lot of coding, but that's the way it goes sometimes, just to try to really understand what to even code and why. So thanks for bearing with me here as we really sort of learn and master the details of register saving. And so, okay. So just to help really solidify the learning. Okay, so the design, let's just call it global register scratch area used for saving, restoring. Convenient because of the global pointer, but broken. And why is it broken? And so number one, interrupt safety. So there's no interrupt safety in the current implementation. If an interrupt happens mid-yield, if an interrupt happens mid-yield and that interrupt handler calls yield, re-enters the scheduler, the in-flight register contents, the in-flight global scratch area gets stomped. And the yield operation that was interrupted will save corrupted, broken register state. I think, and then so as a band-aid, simply disable interrupts during yield. Maybe that is a solution. Okay. Maybe this is a solution, but there's also NMIs to think about. Also, yeah, I'm not saving R flags. That might just be an oversight. Okay, so that is just critically broken. R flags is not saved. And that's not a design issue, that's just a impl problem. R flags is not saved. So that's just something to fix. No segment registers. Okay, this is fine since it's a single ring kernel with no user tasks, but FSGS base are important. Okay, so this is a slightly similar concern. It's just simply, this is not as critical because we're not really using segment registers, but it's theoretically possible. Okay, yeah. SSE, no, we're not using SSE. And so multi-CPU, yeah, I'm not really so concerned about that. And so what does it say? What production kernels do instead? You need a place to save. Yo, what's up, Illusory Moon? Thank you. Appreciate that. Yeah. Today's a little bit of a struggle day getting into the really, like, just the edge of my knowledge. But appreciate that. What production kernels do instead? You need a place to save. The first few registers before you know which task you're saving into. And that place must be per CPU and interrupt safe. And so that's interrupt safe. Okay. What does interrupt safe mean? Interrupt safe means it is a place that won't get clobbered during an interrupt. I'm just gonna note a few of my questions here. Like, it's very tempting to simply disable interrupts as the solution. It's tempting to disable interrupts as the main solution here, but why is that not a very satisfactory solution? I think that's my follow-up question, which I want to ask. Okay. Then it's saying per CPU scratch area, and you access it via GS offset, not a global symbol. Twitch, a lot better than YouTube. Let's popping over onto the Twitch chat. I want more people on Twitch. I do not know how to get viewers on Twitch for the life of me. I stream every single week on Twitch. Straight up, like, no one joins on Twitch. People are more on YouTube, and so yeah. I like Twitch a bit better in terms of its community. It's like it's all built around streaming. Just as you said that 4 people joined. What? No way. Yeah. Anyway, okay. Let's talk about the production solution for this. So it's saying Linux and most x86 kernels do use a small per CPU scratch area, but it's accessed via GS offset. Okay, great. And so the GS thing is a solution for how to find this thing easily. And so this only solves the per CPU is like one aspect to it, to avoid races between CPUs. Okay, sure, whatever. Then there's the interrupt safety thing. And so this by itself, I'm trying to figure out. Yeah, what's up, James? Another solution is to delete everything. Not a good solution, but it is a solution. Absolutely. Yeah, that's always good to keep in mind. You can always just give up. It's always always an option. Interrupt safety comes from the fact that interrupts on x86 don't switch GS automatically. The interrupt entry code does its own swap GS and scratch save. Okay, so here's, I guess the idea is that, so task A is running and it's trying to do a yield. It's like in the process of yielding itself. An interrupt comes in, and instead of like blindly just yielding and corrupting that in-flight yield that was originally happening, the new interrupt is going to kind of swap into its own area, something like this. But what I don't understand about that is I thought the scratch area is per CPU. And so if the interrupt happens on the same CPU that the original task was, isn't it going to corrupt that same memory? So each level, I think I need to ask more about that. I don't quite understand that. Okay, but it was saying apparently there's like option 1 per CPU scratch area, and you use GS to find it. Option B, save directly onto the kernel tasks kernel stack. At yield entry, you just push all registers onto the stack. Task struct saves only RSP. Okay. I feel like feels kind of weird. Okay, so this is saying that tasks just do not save the register contents inside of themselves. They save a pointer to something that lives externally. And that depends on that memory being, yeah, like that somehow feels odd to me. Save directly into the task struct found via GSBase. I do not understand the difference between option C and option A. This is saying store a pointer to the current task in the per CPU area. Or what? It stores one register. Okay, so there's like scratch area for literally one register. So you can save that there, which frees up critically one register. But why can't you just load? I guess, yeah, why can't you just load directly into that area? Can't you just move registers directly into this pointer plus some offset? So the quickest fix is to wrap the yield entry with CLI STI, disable interrupts, and re-enable after blah. That seals the collaborative window without re-architecting anything. The cleanest option is B. Okay, here's the part where I'm going to ask my questions. And so first of all, I'm going to ask about this part. I did not understand this part. I don't understand this part. How is it interrupt safe? Because if the interrupt, because I thought the GS points to per CPU data. So if the interrupt runs on the same CPU core that the original task was running on, don't they share a per CPU global data area, which means that yielding within the interrupt would still corrupt the state? Whoa, got 18 people in the stream all of a sudden. Shout out to the 18 people in the stream. I gotta warn you that we are deep in the weeds of me trying to understand some very fundamental concepts as far as scheduling and saving registers. So I got to warn you that we're not doing so much coding at this moment. We are mostly trying to cram knowledge into my brain. Okay. So this thing I lost. Let me be precise. Why per CPU scratch area? If the voluntary yield path and the interrupt handler use the same per CPU scratch slot, they'd corrupt each other. The key is that interrupt entry and voluntary yields use fundamentally different mechanisms. Okay, interesting. Task calls yield. Oh, okay. Then when interrupt fires, the CPU pushes some stuff. And the interrupt stub pushes the rest of the registers onto the stack. I think I need to draw this out. Sorry, this is sort of breaking my brain right now. So this is our stack, classic stack diagram. We also have the per CPU reg state. Then we have the CPU itself. I mean, we have like just straight up the CPU registers inside the CPU. And then, okay, so maybe let me finish reading this. So the interrupt handler pushes registers onto the stack. So basically, okay, whatever, let's just go back. So first, the task is running over here. And it starts doing a yield, meaning it's over here and it's doing some copies into this region. And it's in the middle of doing this when an interrupt happens. At which point interrupt, okay. The interrupt frame gets pushed, which has the CPU's interrupt frame, and then registers get pushed after that. And so we're in the middle of like right here. We're in the middle of a context switch, which is it's like confusing because it's like two context switches are happening at the same time. In the middle of this context switch, basically another context switch happens, and we preserve the state of the program at this point in the middle of this like running context switch. And then what's it saying? It's like, okay, but like whatever. Okay, so I'm gonna get this thing out of the way. So, sorry. Clear out some of these windows. But it's answering the wrong question. But okay, but the I feel like it's answering the wrong question. The problem was what happens if an interrupt handler tries to yield in the middle of a yield. Okay, I think the main high level point here is that like for the moment, disabling interrupts is perhaps an okay solution. And saves us from this race condition of an interrupt handling during a yield. Maybe we can get more advanced and not have to require that. I think I just still am not understanding. I think I still feel the desire to keep asking some questions here. So but you're answering a bit of a different question, I think. The real problem we were discussing is what happens when an interrupt handler tries to yield. And that is going to conflict with the in-progress yield that is actively using the global scratch area, right? Let's think about that. You're right, now is deflecting. Per CPU scratch area does not solve. If an interrupt fires during and the interrupt handler calls yield, the handler's stub will overwrite the same. Yes, right, exactly. The same when the interrupt returns. Yeah. And so, okay, so the fundamental problem is just this having this like global data, this like global buffer that's used for the registers. I wonder what about, so let's think about this situation though. What if we don't have this global area? So task A is running on the CPU. It starts triggering a context switch, which means it locates its current task and immediately starts saving registers into there. Okay, it's in the middle of doing that. Then an interrupt happens. An interrupt starts running the interrupt handler code, and it triggers. What's the best way to illustrate this? Let's try one of these diagrams. Like I'll call it task A, interrupt handler. Let's try one of these diagrams with all these like downward pointing lines. And so task A is running. I don't know why it's all pink. A is running. A triggers a yield. And so A triggers a yield. It's doing this. It's doing something approximately like this. Start, and let's say it uses GS to locate the task and starts writing registers into it. Then interrupt fires. starts executing interrupt handler code. And then it wants to trigger a yield to another task. And let's have this square represent the shared area. And so this thing is starting to write. It's like halfway through writing into this block. This thing, the interrupt, it's like, okay, timer interrupt happens. We want to switch over to another kernel thread. And so it's going to do, it's going to call scheduler.yield, which is also going to come here. And it's going to do the exact same thing. It's going to use GS to locate the task and start writing registers into it while this thing was in the middle of doing that. And so this thing was like halfway through. This thing comes along and crushes that same thing. And so something is fundamentally like off here. I mean, disabling interrupts is absolutely a solution. And I mean, really the problem is re-entrant, like really the core problem. It's re-entrancy of the yield code. That's the problem. Like in the middle of running this code, we like re-enter it and start running it again. And that is fundamentally a problem if the yield code references the same global state. And so any kind of solution for this would need to make sure that there's like different state being used. And for example, maybe the stack could be used. I'm gonna blow this up huge because this is the key point. It's not re-entrant if it uses global state. To make it re-entrant, it needs to use non-global state, e.g. the stack or something else. But so we could start to imagine what our stack would look like. And I'm sort of learning in real time here. So task A, let's start with task A. Task A is running, it has like some stack frame and it calls yield. And so yield does not really push a new stack frame. It explicitly doesn't do that. And so the stack is not changed during this part of the code. So yield is running, and then the interrupt happens. Okay, let's mark this. Yield runs, but doesn't modify the stack. That's at least what our current implementation happens. Then what happens? An interrupt happens in the middle of yield. So the CP pushes the interrupt frame, and then our assembly stub pushes int stub push pushes the registers. And the registers in question are the registers that were in use by task A as it was yielding. Which really just means task A's last registers, because the whole point of the yield stub is that it's trying to not really modify these registers. So pretty much interrupt is basically resuming task A's state. And then the interrupt handler is running. The interrupt handler is properly running. Let's call it the timer interrupt, because that's a plausible interrupt that's going to try to hit the scheduler and yield. So its handler, we'll call it e.g. timer interrupt. And okay, to maybe make this a little bit less confusing, I'm going to explicitly add a yield frame, even though it doesn't yield frame, just to be clear about what's going on. Even though technically the yield currently occupies no stack, we're exploring the solution space where yield actually could use some stack. And so it's sort of going to look like this. Task A is running. It does a yield, which currently doesn't use stack, but like maybe it could. Interrupt frame happens. Interrupt stub pushes more registers for this thing. Interrupt handler is running, and then it does a yield. And we just walked through why this is broken if both of these yields use the same data area. So let's think about what would happen if they didn't do that. Like, what if they used the stack instead? So what if task A pushes all its state over here? The interesting thing about what would actually happen here if we got this to work is it would allow preemption in the middle of a yield, which is pretty hardcore. maybe more than we need. So yeah, that's like a pretty hardcore thing to allow preemption in the middle of a yield. And so the timer interrupt would happen, and then the yield frame, and then task, like a totally different task would start running. Task B would run, right? Task B could run for some time. But the thing is, task B is going to happen on its own stack. Tasks B already had some stack it was running on. Before, presumably at some point, task B got interrupted, and then task A started running. And then now, after this yield frame, task B is going to run back on its original frame. And then now let's say task B yields back to task A. So we're going to have another yield frame. Task B hits the yield frame. And then what happens over here? We want to basically resume right in this. We want to resume like right here. Long press to unlock. We want to conceptually go after executing the yield frame. We transition back right in the middle of what task A used to be doing, which was in the process of yielding. For the stack-based solution, would it be easier to visualize if the task yield timeline were horizontal and the state of the stack could be represented under each block? Thanks, James. Yeah, that's maybe a good idea. More of like a timeline view. Yeah, I apologize. I'm just trying to think it through in real time. So what's confusing about this situation is then what is confusing is like when the interrupt handler triggers a yield. This is kind of different. I'm going to call this out with a different color. The yield that an interrupt handler is going to do is very different than the yield that the normal tasks are going to do. When a normal task does a yield, its intention is to yield, but then resume. At some point, it wants to resume back from that yield point. When an interrupt handler does a yield, that is not the yield. The interrupt handler is not trying to communicate that it wants to continue execution of the interrupt handler. Really, the interrupt handler is running in the context of the task. And so when the interrupt handler decides that it is trying to yield, it is doing so in service of task A. And that's important. Because that means it's not going to... The interrupt handler is not going to preserve its own execution state in this yield. Yes, yeah, James, I think yeah, we're on the same page. If in the context of task A, taskifying the interrupt handler is not a good idea. I think I'm like slowly getting there. It's like another way of putting it, these tasks are trying to freeze themselves such that they can be like unfrozen later in the exact same spot and keep going. The interrupt handler is not trying to freeze itself for later, really. It is when the interrupt handler, when the timer interrupt runs in the middle of task A running, the interrupt handler is saying, okay, I'm not trying to freeze myself. I'm trying to make sure task A gets frozen. And resumed at a later point. So the interrupt handler basically doesn't care about itself. It sort of like sacrifices itself and is going to do whatever it takes to make sure that the task A state gets preserved. And that's going to mean something pretty different. Instead of doing this like pushing the registers thing, it's going to locate whatever context was pushed by the CPU, indicating task A's state. And it would need to use that to populate the scheduler state. Interesting. Okay. Whoa, I think that was kind of interesting. I'm gonna take a couple notes just to capture my thoughts, but I've been talking so much. I need a bit of water. Let's all. I'm just gonna take a quick. Let's take a 20 seconds. Okay. Thank you for bearing with me through this sort of brain melting experience. And so let me recap everything that I feel like I've learned just now. And so let's zoom out like 10,000 feet. What are we talking about? We're talking about interrupt safety of cooperative scheduling. The question is, what happens if an interrupt happens in the middle of a cooperative scheduler yield? For example, e.g., if a timer interrupt happens and we want to schedule a new task while another task was in the middle of trying to schedule itself out, right? And so, first of all, I think the important thing to say is that I don't know how real of a problem is this. Is this really a problem we want to support? Trivial solution, disable interrupts while in yield. Simply disallow. Simply disallow interrupts. Basically, do not support preemption in the middle of a yield. Supporting, it comes down to this. Do we want the OS to support such a level of preemption where you can even preempt the middle of a yield operation? I think it's reasonable to say no. I think I don't know how modern or production OSs do it. Maybe they do allow this, but for my purposes right now, I think it's actually reasonable to just simply say we don't. Like, that is a pretty extreme level of kernel preemption. Okay, so first of all, it's reasonable to say, no, we don't support this extreme level of kernel preemption. There are probably even other considerations that I have not even thought about, but this actually sounds kind of tricky and maybe even dangerous. Like, this even sounds dangerous and risky potentially. Concurrency, locks, etc. James has this idea of an infinite series of preempted yields. I mean, I think the one saving grace for that particular case is that if the preemption happens because of the interrupt, typically, I don't think another timer interrupt can preempt an existing timer interrupt handler. I think the interrupt controller like sequences them. So, but that's a little bit of a guess. What's up, Indie Whip? No problem. Yeah, you are a little bit late. I need to probably wind down the stream in a little bit, but yeah, we've just been like deep. I've just been trying to really understand scheduling and stuff like this, and it's been kind of difficult. But I think we made some progress. Actually, I mean, I definitely understand this better and understand the design space around this better. And so let me keep writing down my thoughts. And so we're talking interrupt safety of cooperative scheduler. So first of all, do we even want to support this? Like, no, probably not. It's probably reasonable to not support this. Okay, but let's say we wanted to go super hardcore and actually support this preemption of the scheduler. Sure, yeah, IndieWeb. If you have some lessons you want to share, I'd absolutely welcome that. Yeah, I feel like I'm doing a lot of learning here for the first time, and so I could appreciate any guidance at all. I will just keep writing out what I learned. So let's say we wanted to go super hardcore and actually do this. The way it would work, I think. So first, fundamentally, the interrupt handler that does the yield needs to do something different than a normal task that's yielding. It's executing in the context and service of a specific task. It's not trying to restore its own interrupt handler state. It's restoring the original state of the task, which has been pushed on the stack by the CPU. So it needs to populate the task register state from the CPU state, which is not normal. The headache inducer branch. Crazy. Okay, so that's an initial observation. That was like the end outcome of this thought process. This yield from IH needs to be fundamentally different and populate and fill the task reg state from the CPU pushed register state. Which I think only solves one part of the problem. Like, so we've identified that this needs to, the mechanics of this are kind of different. It's going to actually you know what, I wonder. Okay, I don't know. I was thinking some weird ideas, but basically we're trying to. Okay, I'm gonna say my weird idea. I don't know how it sounded this, but I wonder if would it be possible for the interrupt handler to preserve the state of the thread actually at the start of this stub. So even though the task A might be in the middle of here, maybe the interrupt handler just sort of forces the task to restart execution from the start of the stub, potentially. I don't know if that sounds, but basically there's still this question to answer. It's like, oh, how? Okay, so we know that we need to restore the state from this context on the stack, but the question remains of where do we store it to? This global buffer or like what? And okay, so what would that look like? And so the CPU was in the middle of writing its registers into this area. It got preempted. That state of things is frozen in terms of the CPU pushed registers. So how bad would it be if we were to could that work? The yield for like this special operation, what if it's basically just copying this data, these CPU register data, into the task A structure? Okay, let me see. So back to this diagram. Task 2. So I think the general flow I'm envisioning here. So starting task A, it's doing its thing. It's in the middle of these copies. It's like in the middle. It's like on this instruction. And theoretically, this is the state we want to preserve and resume from here. We get interrupted. The interrupt handler is running and it triggers its own interrupt handler yield. What would happen if we just took that state that's on the CPU and we copy it directly into the task 2 reg area? And so we copy it directly into the task 2 register area. Because in this context, we're not really so constrained. We can pretty easily access the task structs and everything. So let's just say we just like take the stuff, copy it directly into here. And then that is pretty much it. We schedule another task and we resume task B. And then task B does the normal resume of like the normal yield API to go back to the other task. We've frozen some particular task state into the registers here, and that is going to be what gets unpacked and executed. And it's basically and it's going to be this register state, which is pretty much by definition, the register state that this task was in, at the point of stopping. So I feel like there are some possibility. I'm going to check the chat. Okay, set up a little lesson on the Discord and post some customers. I'm confused whether you're doing timer to preempt or yield. And so it's like both. It's so the plan is to eventually support preemption. And so what we're talking about is, but the yield and the preemption can coexist. And so we're talking about the intersection of these two things. What happens if the preemption happens during a yield in DWIP is what we're talking about. So let me blabber a little bit to the AI and have okay, here's a bit of a crazy idea. About how to support preemption of a yield process. And so the situation is task A is in the middle of doing the preemptive yield, and then all of a sudden a timer interrupt comes in. Here's the idea. What if the interrupt handler, when it goes to do the yield, it uses a special API that copies the register state that has been pushed on the stack by the interrupt, which is by definition the frozen state of the original task. Let's call it task A. What if the interrupt handler copies that state directly into the task struct for the task A, and then triggers the yield to task B? It seems to me that when task B triggers the yield back to task A, the state in the task struct of A will be unloaded. That state will correspond exactly to what the interrupt handler had pushed originally, which should have perfectly preserved the execution state of task A, even while it was in the middle of doing the yield. And it seems to me like that should actually seamlessly resume the original execution of task A in the middle of the yield. What do you think about that? Let's see if it understands me, and then probably I'll have to start wrapping things up pretty soon. I'm just discussing the AI, my idea. I think probably in the end, even though we thought through all of this quite in depth, I'm probably just going to wrap it in a disable interrupt. I'm probably just not going to support this level of preemption for the moment. It is talking about complications. Okay. Apparently my approach is broken. Task A. If task A is interrupted during normal task execution, my idea is correct. Hardware pushes a bunch of things. We copy that frame into the struct. Okay, so that seems to work. But what mid-yield interrupt, the handler saves the frame into task A struct, right? Switch to task B, switch to task A. A resumes mid-yield, and calls that. Task A yields again immediately. Task A gets requeued. Oh, interesting. Wait, that's actually is that interesting? Task A gets requeued. With a saved rip still inside the stub. I think it's right, actually. Yeah. So my idea was a little bit full. That's actually really, really good thinking. So the problem is that, okay, so the idea was like, okay, the interrupt handler copies the push register's state directly into this thing. And then the problem is that the rip at this point corresponds to like in the middle of here. That rip is going to get saved into here. And then the next time task 2 gets scheduled, for example, when task B or goes back to task A or whatever, we're going to re-enter right here. But the problem is we're just going like, okay. The rip that gets saved is going to be like kind of weird or something. The rip. Oh no, yeah, it's not. No, the rip that gets saved. Wait. It's important to have the full context. Oh my gosh. Sorry. So, the full context. The rip that gets saved into the blob is no, it's the original rip from where task A should return to. So I don't know if I actually understand that. It's saying task A gets requeued with a saved rip. Re-enters the scratch save sequence. Scratch save runs to completion and calls blah. Task A yields again immediately. Task A gets requeued with a saved rip still inside the stub. And then it's, okay, then it's saying there's this problem. I'm not sure that's right though. Wait, it's real kernels with a problem. Strictly non-overlapping. And so they're basically, okay, this is like, they're basically saying this is like messed up. But I think, I don't understand number 6. Oh man, I've reached my daily 3-minute transcription. Okay. I don't understand this. When it re-enters the save registers sequence, it's going to save to populate the rip in the task struct by reading the stack, which points to the rip of the first instruction in the real task A that should be resumed. So I don't actually see how the saved rip in the stub would be requeued. Let me just ask that. Yeah, one quick thing you can do is call CLI during the yield to make sure the timer interrupted. Yeah, that's a great point. I think as much as I'm thinking through this right now, I think that's probably the practical solution to do. It simplifies things a lot and sort of it just reduces so much complexity. And so I think that's probably the practical thing to do. I think just right now, it's an interesting challenge to think through what it would take to support preemption of the yield, but it's a little bit too much. So this might be my last exchange with the AI. Okay, I'm forcing the AI to do a bunch of thinking about this stuff. You know, I don't have... Oh, wait, why am I not using Opus 4.6? Maybe it could think through this a little bit better. Okay, this is not looking good. I'm seeing it saying there are bugs here. I'm seeing it. It looks like it's trying to solve it with that weight. Okay. Oh man, it's really doing some cognition. I probably should have been using Opus 4.6. I didn't realize that I had it available. Okay, human versus the AI. My melted brain versus what the AI. You're right, and I was wrong on that specific point. Let me correct it. When task A resumes mid-stub, the stub continues forward and hits. Move racks, blah, 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 load that into here. The stub doesn't rerun from the top. It resumes mid-execution. The RSP was restored to exactly what it was before the interrupt. So RSP still correctly holds RIP A. My claim about getting stuck with a stub ripped was wrong. What the scheme gets right, the early saves are already in Scratch. The register's task A resumes with exactly that interrupt captured, what the interrupt captured, which are task A's true values at that point, since the stub only writes to racks. And racks was already saved, but the scheme breaks the double yield. A takes an extra trip through the scheduler every time it gets preempted mid-stub, which is true. The current task, when the interrupt handler saves task A, some index moves to task B, but task A resumes mid-stub and calls this thing. That function calls current task. Oh, shit, that's a problem. Wait a sec. Presumably moves, but A resumes mid-stub. Okay, it's saying, I hope this gets resolved by the time I get around to opening a text editor to start writing my OS. Yeah, just hit me up when you do, and I'll tell you everything I've learned. I think we are actually somewhat close to resolution. This point is garbage. That's like irrelevant. I know that's just a simple implementation issue. OpenStack. I mean, really, if you want to start writing your OS right now, the simple, stupid answer: disable interrupts before the yield. we are just doing a bit of like mental gymnastics right now to see if what it's like to try to do even a little bit quote unquote better than that when and I think actually the AI is starting to admit that my idea kind of works. Or rather the idea that we have been collectively ideating here. But let's just think through this one last point. The current task. And so what it's talking about, I just have currently, it's like this pretty stupid like integer that corresponds to the index in this array of the currently running task. And so the interrupt handler saves frame and switches to task B via something along the lines of, I mean, the way we currently do it in the scheduler is something like here. When we switch to the task, we pick a task index, we assign this index to whichever index. And so it's it's like the state of the currently running task, right? And so it's saying, this thing presumably moves to task B. But when task A resumes, good luck, James. Fair one. Get ready for keyboard smashing and head throbbing. Pretty fun when it works, yeah. Today has definitely been a keyboard smashing stream for me. Okay, but when task A resumes mid stub, but let's think of, I don't know if that's right. But when task A resumes mid stub, but the thing is, how is task A going to resume? Task A is going to resume when task B calls yield, which triggers this execution path. Which triggers yield impl, which chooses the next task, which is going to be task A, comes in here, and it's going to set MO current running index to task A's. And so I don't really see what the problem is. I'm going to call that out. And so that function that calls current task, at that point in time, task A is running, so the pointer should be right. I'm going to call this out. Okay. But is there a problem? Task B would presumably use yield impl switch to task A, which takes care of setting to task A's index. So by the time task A executes, the is totally consistent. I'm going to call that out. You're right, there's no problem. Let me verify. I was wrong to flag it. The bullet point can be dropped from the list of concerns. Okay, so we got rid of this one. This is not really a problem. The double yield, whatever, that is just a property of making this work. This is not a problem. This is not a problem. Orphaned interrupt frame. The 40-byte interrupt handler push below is abandoned when you context switch instead of IRET. Okay, that's interesting. So what this is saying, it's like, okay, it's going back to here. So there's this frame, And what we actually do is we never iret. The proposed solution never irets. It forcibly context switches to another task, which I actually don't really know how. I don't necessarily know how safe that is to do, so that's a genuine question from me. Is it actually safe to never iret queue from an interrupt and context switch like I propose? Or do interrupts always need to be iret queued? So that's genuine knowledge that I'm missing. James's OS is somewhere on the external hard drive. We'll be restarting from nothing again on retry. Nice. Indie Whip saying, quick tips, start writing your own FS early. I would say it's a lot of code. It's a lot of code. I'm doing a FAT16. It's already 1,000 lines of code. Dude, yeah, file systems, complicated stuff. Does anyone here know the answer to this question? Actually, I just don't. I'm not so deep into the iret queue. I know, it's obviously possible to iret queue to return after an interrupt, and that's probably what we want to do most of the time. But I'm thinking about this specific case where we are trying to do a timer interrupt, and that comes in. And we want to schedule to something else. And so do we necessarily iret queue? If we, you need to handle what the iret queue does, but you don't have to use the instruction itself. What does iret queue does? Pop rip, pop CS, pop R flags, pop RS. Okay. R flags. When the CPU takes an interrupt, it automatically clears IF. If you skip iret queue and context switch to another task without restoring R flags, the task runs with interrupts permanently disabled. So that's actually important. That would be a problem. I'm just gonna put this here. Problem. If we don't iret queue, we need to be very careful to recreate what it does, specifically re-enabling interrupts. Okay, that's interesting. Standard solution, even when doing a context switch out of an interrupt handler, most kernels still use iret queue as the mechanism to restore the target task's state. They construct a synthetic interrupt frame. Right, okay, so that would be an implementation detail here. And so an implementation detail of this special interrupt yield. So impl detail, when the IH does the special yield, not only does it copy the task state from the stack into the task struct, but also synthesizes a IRET frame to jump into whatever task is scheduled next. So that's interesting. So when it wants to, when the interrupt handler wants to jump over into task B, it's not really going to do the typical way these two tasks usually switch. It is going to do a slightly special way, like a slightly indirect way of doing that, where it actually uses an IRET queue to kind of jump back there instead of doing the push ret trick. Instead of doing the push ret trick that we do right here. The push ret trick is just a way to like jump to another PC like arbitrarily, and IRET would be another way to do that. The secondary mandatory concern is end of interrupt. It has nothing to do with IRET. It's a separate right to the interrupt controller that must happen before you return from any interrupt. If you skip it, the interrupt controller thinks the IRET line is still being serviced and won't deliver interrupts. So my takeaway from all of this is actually that like this idea I had, I think could actually work. A separate API specifically used by interrupt handlers that want to yield, which does a few special things. It needs to copy the state in a special way from the stack into the task drop. It needs to specifically, when it chooses the next task, instead of like jumping directly into task, it uses the synthesized IRET queue. And then it also takes care of handling the EOI, the end of interrupt. But assuming all of that happens, theoretically, that would be a way to do it. And we could have our absolute insanity of supporting preemption in the middle of a yield, which frankly is probably opening up myself to a world of pain in the future. But theoretically, that is how it could be done. All right. Insta Headshot is asking, is Claude Sonnet paid? I think so. I mean, I pay for it. I don't know if there's a free version for use in VS Code. There might be. Sorry, I don't actually know. Cool. I am going to wind. Yeah, I need to head out. But I want to thank you all very much for watching this stupidly involved stream of me going very deep on trying to understand interrupts and preemption and scheduling. And next time, well, okay, so first of all, here's the Discord. Feel free to join if you'd like to keep chatting. If you like this content, please subscribe to my channel. That would be super helpful. And next time, we're going to actually continue. I think what I'm going to do, I'm just going to implement the stupid way of disabling interrupts. That's just going to be the solution there. And okay, so take some notes for next time. Implement the CLI STI solution for disabling preemption during a yield. And probably implement this FSGS based strategy for per CPU state then store a pointer to the task struct in there, and directly store the state in there in the ASM stub. Okay, those are a couple ideas for next time. And with that said, I'm going to sign off. Thanks a lot for joining the stream today, everyone. And I hope you have a great week, and I'll see you in the next stream. All right, peace.